Okay, great. We know how to quantify the amount of heat or thermal energy Q that is transferred in a heating process that changes temperature. But what about a process like this? Here, we know that there is still energy flowing out of the water as it turns from water into ice and into the cold, cold freezer. And yet the temperature is not changing at all. So somehow or another, heat is flowing out without the temperature changing. This is known as a phase change. And obviously, we can't write the change in temperature or the heat in terms of a change in temperature because there is no change in temperature. But there certainly is energy flowing in or out in a freezing or melting situation. We call that energy the latent heat, or simply heat of transformation. So let's make this a little smaller. And the formula is simply that the heat, or the energy in the heating process, is just the mass times the latent heat, or the heat of transformation. Sometimes people will put a plus or minus here. It's plus if energy is going into the system, it's minus if energy is coming out of the system. So for example here, where we're freezing, the temperature of the freezer is less than the temperature of the system, we would have a minus because energy is coming out of it. If we were melting, we would have to have the environment be warmer than the system, and it would be a plus because we would be adding energy to the system. So let's come down here and let's pull up our chart. So here you see is a chart of various latent heats, heats of fusion, and heats of vaporization. Fusion is when you're going between a liquid and a solid. It's called freezing when you're going from liquid to solid. It's called melting when you're going from solid to liquid. And vaporization is when you're going between a liquid and a gas. It's called evaporation when you go from liquid to gas. It's called condensation when you go the other way. All of them can be positive or negative depending on which direction you're going. Notice these are large amounts of energy. If you look here for melting water, 333 kilojoules per kilogram, or in other words, 333,000 joules per kilogram. When you consider it's only a little more than 4 joules per kilogram to raise it 1 degree Celsius, it turns out this is equivalent to raising the temperature close to 80 degrees Celsius. Heats of vaporization tend to be even larger. Tremendous amount of energy required to evaporate water. Now you may be led to ask, why can we add energy and sometimes change the temperature and sometimes not change the temperature? In particular, if we don't change the temperature, where is that energy going? Well, we will talk about this more in the next chapter, but to understand it a little bit right now, let's go back to a block in macroscopic physics. This block could have energy by virtue of its motion, which we call kinetic energy. It can also have energy by virtue of its position, say it's very high up. We call that energy by virtue of its position, potential energy. Or it could have energy if I drew a little wall here with a spring. Then if I compressed it up against the spring, I could get potential energy because the spring is compressed. Well, it turns out that at the atomic and molecular levels, we have these same two kinds of energy. We have energy associated with the motion and energy associated with the potential energy from individual atoms or molecules being linked to each other by links which are a lot like springs. Now, in general, both of these can change. But when we're raising the temperature, we're mostly changing the kinetic energy. And kinetic energy is what is tightly related to temperature. When we're changing phase, we're making a dramatic change in the potential energy. Even when you keep the same phase, there's generally some change in potential energy, but it's a very dramatic change in potential energy when we change phase. So for example, when we go from a solid to a liquid, in a solid the atoms are all tightly linked together here, whereas in a liquid they break those tight links but still move around each other in a fairly close formation. So they still have a lot of interactions as they move all around. We have an even more dramatic change in potential energy when they go from a liquid to a gas, where they're all essentially free from each other, and nearly all of this potential energy, or the negative potential energy of holding them together, has been lost. So that's why we have large amounts of energy that go in without a change in temperature. Dang it. So what's happening is we can change the system's microscopic configuration by letting the molecules move further apart or change the way they interact. That's a change in potential energy and is not associated with the temperature change. We can also change the system's energy configuration by changing the kinetic energy or thermal energy, letting the atoms and molecules move faster, and that is associated with a temperature change.